So this will be the video that will begin to deal with the A-star search already. So when we say A-star search, that is a algorithm which is widely um, used informed search algorithm for path finding and graph traversal. Its actually primary goal is to find the shortest or least cost path from a start node to a goal node in a weighted graph. So therefore, if in our really best first search we're dealing with the f of n, but here now you will deal with the g of n as well as the f of n. So there will be calculations that will happen pertains to that one. So it is notable for its completeness, optimality, when the heuristic is admissible, and efficiency, making it a standard in fields like artificial intelligence, robotics, and game development. So in this case right now, it combines the Dijkstra's algorithms and greedy best first search, is what I mentioned, by considering both the actual cost to reach a node from the start, which is the g of n, the value of those, um, what we call this one, those weighted graph, and an estimated cost from that node to the goal, which is the h of n, provided by a heuristic function. So that's it. That is the function for the h of n. So where you will use the algorithm will evaluate nodes using that functions right there, the f of n is equals to the g of n plus the h of n. So there will be a calculations that will happen after later on. We'll begin to deal with that step-by-step process. Where your g of n, that is the cost for the from the start node to node n. And h of n is the heuristic estimate of the cost from n to the goal, and f of n is the total estimated cost of the cheapest solution through the n. So we'll be going to deal with that step by step, and there will be a specific steps that we will be going to follow with, especially first will be the initialization after the main loop. Then you have to repeat um, what we call this one. Repeat until the path is found or open list is empty. Then explore neighbors of current, then termination, the path reconstruction. So in this case, we'll begin to deal with it. When we say initialization, this is the place, the start node in the open list, a priority queue sorted by f of n. So this is a setting or initial state in your graph or in your tree. Then g of start is equals to zero, then cost from start to start. So h of start is a heuristic start, and f of start is equals to the g of start plus h of start. That is how you will deal with this. So create an empty closed list, then set of already evaluated nodes. This is how it works in initialization. Afterwards, the main loop will start. Repeat until path is found or open list is empty. Selecting the node with lowest f of n, remove the node current from the open list with the lowest f of n. So until that you will be going to be, find the goal um, node. So goal test if the current node is the goal node, reconstruct and return the path from the start to the goal. That's how you will deal with that one. And for the main loop, repeat until the path is found or open list is empty. Move to the closed list. Add current to the closed list so it won't be re-evaluated. So that is the main loop. And afterwards, explore the neighbors of current. For each neighbor of current, skip if already evaluated. If the neighbor is in the closed list, skip it. Calculate the tentative, the G of current plus the cost of current neighbor. That's how you will deal with that one. Add or update an open list. If the neighbor is not in the open list, add that. If this path is better, lower G than the previously recorded one, update G neighbor is equal to the G tentative. H of neighbor is equal to the heuristic neighbor F of neighbor is equal to the G plus H. So set parent neighbor is equal to the current for path reconstruction. That's how we will deal with that. After will be determination if the open list is empty and the goal hasn't been reached, report failure, no path exists. Of course, if you were not able to find the goal node or if there will be no direction or if that is not there. So you can definitely just report that no path existing to up to the goal node. Then path reconstruction start from the goal node and trace parents back to the cert. Return the list of nodes is the final shortest path. I really forgot, by the way, in your heuristic greedy best first search was not able to draw the final graph that you will begin to reconstruct, but I will begin to deal with a star search already so that you could be able to base that here. How will you able to reconstruct the graph or the tree? Then the time complexity depends on several factors. The quality of the heuristic H-van, the branching factor is B, the depth of the optimal solutions is D. So whereas your best case is O notation of D, if the heuristic is perfect H-van, always exactly equals the actual cost, the cost to goal. ASAR behaves like the Dijkstra's algorithm with a shortcut visiting only the nodes on the optimal path. So that's why it is a best case. And for the average case, that is O notation of B to the power of D when using an admissible but not perfect heuristic. A star explores more nodes, but still fewer than the uninformed search, where your B is the branching factor, the average number of children per node, D is the depth of the optimal solution. So this is somewhat often the practical cost unless the heuristic is somewhat strong. So for the worst case time complexity, that is still O notation of B to the power of D. If the heuristic is 4 or 0, like degenerates into the uniform cost search, A star explores all nodes up to the depth D. That's why. And for the space complexity, it is O notation of B to the power of D, whereas A star maintains the open list priority to frontier nodes and a closed list visited node. Since it stores all generated nodes in memory, space usage is high. So that's how it worked for the A star search. And I'll be going to deal with the step by step of A star search in the next video. Thank you so much, and see you in the next video then.